Hello everyone, my name is Xulin Zhou, and I'm a graduate student at the Institute of Software, Chinese Academy of Sciences in Beijing, China. Today, I'm very happy to share with you our latest work on a novel SIMD library called HybridSIMD. SIMD is an optimization technique that is critical for CPU performance. It is the primary method for achieving vectorization at the hardware level. And currently, there are many approaches for developers to use SIMD. Our focus here is the programming with SIMD libraries. The figure on the right shows an example of the SIMD library I mentioned above, and it provides a high-level C++ abstraction on top of low-level entrances. So using a SIMD library is very convenient for writing vectorized programs. But the thing is, there are too many such libraries, HybridSIMD, XSIMD, TSIMD, etc., etc., and each has its own internal design and performance behavior, which bring us two main problems. First, it causes performance fragmentation when there are too many SIMD libraries. Our preliminary experiments show that for complex programs such as breakthroughs, the choice of libraries has a significant impact on performance. So developers have to benchmark multiple libraries to find the best one, and which is very time-consuming and unscalable. And second, too many SIMD libraries also cause usability fragmentation. As mentioned above, the choice of library has a clear impact on performance. However, as we can see from the table below, different libraries use different function names and different semantics. That means developers must constantly relearn new APIs, which hinders productivity. So what can we do in the face of such fragmentation? First, there are some options we can consider. And the first one is that we could keep only one library, but that will lose the performance opportunities offered by other SIMD libraries. Or we could create yet another new library, but that will only increase fragmentation. So our key idea is that instead of keeping just one or creating another, we embrace the idea of collaborating them. By collaboration, we can not only leverage their complementary strengths to solve performance fragmentation, but also provide a unified abstraction to solve usability fragmentation. The idea leads to our solution, HybridSIMD, a SIMD library with collaborative auto-tuning. The figure on the right gives an overview of that system. HybridSIMD takes a vectorized C++ program as input and outputs an optimized binary executable. The system has three key parts: a unified interface for developers, a front end for building the search space, and a backend for auto-tuning. And we will take a look at them in order. Okay, first, let's start from the unified interface. Our goal here is to support different SIMD libraries under one umbrella. And to do this, we classify existing SIMD libraries based on their support for two types of vectors. Here, the claim built-in vector types can be understood as an abstraction of the intrinsic type, but with an interface that exposes a configurable vector element count. This is an example of how to use our HybridSIMD unified interface. The SIMD operations showed in the rec box use three template parameters. the element type, the vector length n, and the SIMD library type. This design enables a common interface without breaking the underlying semantics. Okay, after talking about the user interface design, let's move on to the front end. Its job is to generate a search space for tuning. Oh, how to do this? We first perform static analysis on the input program to extract key information useful for generating the search space, as shown in Figure B. And then we apply rule-based pruning based on unsupported operations and the conditions on vector element counts. This proving step makes the subsequent auto-tuning process much more efficient. However, even after pruning, the search space could still be enormous. So in the backend, we use hierarchical tuning to reduce search time. And the key idea is that we prioritize the tuning of the most impactful parameters before optimize others. The tuning proceeds hierarchically, and we first fix the parameters that have the greatest impact on performance. Then we tune the next most significant ones based on that. And for the remaining parameter combinations, we just employ a genetic algorithm to reduce the search space. That's what we do in our backend. Okay, after introducing the HybridSIMD to verify the effectiveness of our system, we tested HybridSIMD on 3 SIMD platforms, and we use 6 diverse HPC benchmarks, ensuring they cover core operators across different domains. Results show that the HybridSIMD achieves up to 185 times speedups compared to the scalable version across 3 platforms. And the pursuit of peak performance justifies the tuning process. We also look at a case study of the peak benchmark and concluded that the generating machine code shows major benefits from loop fusion, simplified control flow, and enhanced parallelism. So together, this explains much of the observed speedup. We also perform calibration studies to validate our hierarchical tuning and the tuning parameter priority. Okay, here are the takeaways finally. Fragmentation can be addressed effectively through collaborative design, and the dynamic nature of performance factors necessitates auto-tuning. So motivated by this, we propose HybridSIMD, a collaborative C++ SIMD library integrated auto-tuning. Nevertheless, portable existing codebase to HybridSIMD still requires manual effort, and integrating multiple SIMD libraries increase binary size. And so that's how we address these problems remains to be our framework. Okay, thank you very much for your attention, and feel free to reach out to me if you have any questions.